Hi, physics. Mr. Janowski here. This is chapter 13, homework number 3, problem number 2. So this is going to be another problem that deals with Newton's version of Kepler's third law. So the situation is we have some communication satellites that are in what's called geosynchronous orbit. So geo meaning Earth, synchronous in sync with, meaning they take exactly 1 day to orbit the Earth. So we've got to figure out a few different things. So let's see. Yep, wrong tool. Things we need to figure out. Step, For part A, how many seconds are in a day? All right, so I'm going to call that T actually, because that is the period at which these things orbit. So T is equal to question mark seconds. For part B, how far from the center of the Earth does a geosynchronous satellite orbit? So what we're actually looking for is the radius of the orbit. So remember, when you're dealing with a sphere and the Earth is a sphere, you need to measure your distances from the center of the sphere. So that's why that question is phrased that way. So R is equal to question mark meters. And then part C, how high above the surface of the Earth is this? So that's the height. Height is equal to question mark, and that will also come in meters. So first things first. No, this isn't the first thing. This is not the first thing. But part A. Yeah, we need to figure out how many seconds are in a day. So let's start with this idea. T is equal to, we can even start here, 1 day. So we need to get out of days and ultimately into seconds. So let's start by getting out of days and into hours. So how do I get out of days on the top? I put days on the bottom and hours on the top. And how do these guys relate? Well, 1 day is 24 hours. Then I need to get out of hours and into minutes. So hours on the bottom, minutes on the top. 1 hour is 60 minutes. And then out of minutes, so minutes on the bottom, and into seconds on the top. So how do these guys relate? 60 seconds is 1 minute. So if we were to follow the units, day on top will cancel with day on the bottom. Hour on top will cancel with hour on the bottom. Minute on top cancels with minute on the bottom. And the only unit we have left is seconds. So what you have to do in your calculator is take 1 times 24 times 60 times 60, and then divide by 1, divide by 1, divide by 1. And if you do all that, you'll get this number, 86,400 seconds. So yeah, it's 2020. You could always just ask Google how many seconds there are in a day, but that's not going to work when you're taking a test. So you need to be able to do you need to be able to do this kind of problem. So now, how far away from the center of the Earth does a geosynchronous satellite orbit? Okay. Let me scroll down just far enough to give me enough room that I can do this. Switch to a nice green color. So, yeah, what we're going to do here is use Newton's version of Kepler's third law. And I'm going to recommend, again, using the pretty version. So this squared over GM R cubed. So in this problem, we know T, that's what we just figured out in part A, is the period in seconds. What we're trying to solve for is actually R. So the way to do this is first solve for R cubed. So how do I do that? I'm going to multiply both sides. Let me just write the R cubed part. So I'm switching left to right. I'm going to multiply both sides by GM. And that's going to give me GM T squared on the top divided by, and I'm going to divide both sides by 4 pi squared. So now I have that. So what is my M? My M is the mass of the Earth. So that's this number right up here, 4.97 times 10 to the 24th kilograms. And G is G and all the other things. So let me get a little bit more room to actually do this. So this would give us r cubed is equal to 6.67 times 10 to the minus 11th. That's your constant for g. The mass of the Earth is 5.97 times 10 to the 24th kilograms. So that's the m part. And now we need t, which is our answer for part A. You've got to get it into seconds for this to work. So that's 86,400 seconds. And that part gets squared. Only that part gets squared. And then on the bottom, we need to divide by 4 pi squared. Now, it may help you when you're doing this to get the order of operations right. Maybe throw a big parentheses around everything on the bottom. Again, until you get really good at the calculator, there's lots of ways to mess this up. So, again, one way you can do it is just figure out the whole top, turn the whole top into a number, figure out the whole bottom, turn the whole bottom into a number, write those numbers down separately, and then do the math separately at the end. But if you get good enough at the calculator, you will eventually be able to do this all in one shot. So if you do all of this, so 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24th times 86,400 squared divided by 4 divided by pi squared, then what you're going to get is a big number. Let me see, I have the number written down already. So you're going to get 7.5295. I'm running out a lot of digits here. Times 10 to the 22nd. So is this our answer for r? This many meters? No, it is not. This is our answer for r cubed. Oop, r cubed is this. So this is actually the answer in meters cubed. And it's hard to, we don't deal with numbers like this every day, but this is a huge, ridiculous number. This is far too big to be our answer. So what we need is to get the cube root of this. So how do you get the cube root in your calculator? Well, one way to do it, so over here, I'll draw what we're going to do. This, so that's how you can write cube root. A way you can do this is take the answer you just got and then raise it to the 1/3 power. Because taking something to the 1/3 power is the same thing as taking the cube root. So on my trusty TI-36X Pro, the way I would do that is I would hit the X to the box button and then do 1 divided by 3 and then hit enter. So that's one way to do it. So if you do all that, what number do you ultimately get? You get a number for r of r is equal to 4.22 times 10 to the 7th meters. And that's a much more reasonable number. Still a big number, but it's much more reasonable. So there's our answer for part B. Now for part C, remember the last thing we need to figure out is how high above the surface of the Earth is this? So here's what's going on for this. So here we are, part C. So you've got, and I'll draw to make it actually look like high up and down, although it is kind of meaningless in this context. So you've got the satellite. So here's a satellite. Maybe he's got big old solar panels on him. So something like that. And the distance we just figured out was this distance, the distance to the center of the Earth. So that was 4.22 times 10 to the 7th meters. And we're calling that r because that's the radius of the orbit of the satellite. So the question is really, what is this distance? Well, I don't want that. Now my computer's freezing up. Come on. Trying to do undo, and it ain't undoing for me. Oh, come on. This was such a pretty picture before that. No, stop it. Did I change tools or something? Oh, that's annoying. There we go. Okay. What a nightmare that was for a second. I was going to have to abandon this video all the way at the end. So the height we're trying to figure out is this. So this is the height above the surface. So what is this height going to be? Well, it's going to be this r, the radius of the orbit, minus this r, the radius of the Earth. So what we have is height is equal to radius of orbit minus radius of the Earth. So h is equal to, again, the radius of the orbit is 4.22 times 10 to the 7th meters minus the radius of the Earth. And if we go back up here to this table, the radius of the Earth, so not the radius of the Earth's orbit, that doesn't factor into this, the radius of the Earth is 6.38 times 10 to the 6 meters. So minus 6.38 times 10 to the 6 meters. So do that in the calculator, and what do you get? You get 3.58 times 10 to the 7th meters. So there you go. And that's a more reasonable height. So hopefully you guys are finding this helpful.